Hey everyone, let's jump right into this explainer. Today we're taking the abstract, sometimes intimidating physics of thermodynamics and we're bringing it right into your living room. We spend our entire lives surrounded by temperature changes, but by the end of this, you're going to clearly see how those invisible scientific principles connect directly to the everyday appliances you rely on and the very physical sensations you feel every single day.
Here's our roadmap for the explainer. First, we'll cover the nature of heat. Second, measuring the invisible. Third, the science of refrigeration. And fourth, thermal systems and power.
Section 1. The nature of heat.
So what are we actually talking about? Thermodynamics. It sounds like a heavy textbook word, right? But really, it's just the ultimate rulebook for heat and, more importantly for our modern world, how we convert that heat into useful work. It's all about how we force energy to behave and harness it to do incredible things.
You know that feeling when you step outside on a freezing winter day or a scorching summer afternoon? Well, heat and cold aren't just random sensations your brain makes up. They are literally your physical, bodily reaction to different energy states. When we say heat, we're actually just describing the effect of high energy content. And cold? That's just what low energy content feels like. It's all about the presence or absence of that energy.
Now, where does this energy even come from? It all traces back to something called internal energy, which engineers represent with a capital U. And this is wild. Internal energy is literally the sum of all the tiny, microscopic motion happening inside a substance. So even if a solid block of metal looks perfectly, completely still to the naked eye, deep down, its molecules are in an absolute frenzy. And that microscopic motion? That equals energy. On top of that, every single substance in the universe, whether it's a solid, a liquid, or a gas, has what we call a heat capacity, represented by a capital C. Think of it like a built-in storage tank. A piece of iron, a swimming pool, the air you're breathing right now, they all have their own unique innate ability to hold on to thermal energy.
Section 2. Measuring the invisible. Since we can't actually see this energy with our own eyes, how do we track it? Well, human ingenuity is pretty amazing. We measure temperature using three main tricks. We watch for a change in physical dimensions, we measure shifts in electrical properties, or we read the thermal radiation an object is giving off.
Let's zoom in on that first one. Changes in physical dimensions, also known as thermal expansion. As internal energy ramps up, all that microscopic motion gets faster, and materials physically swell up. I'm talking structural steel, copper tubing, industrial piping. They actually grow in length when they get hot. It's a huge deal for engineers. They literally have to build pipelines with extra room just so they can stretch out.
And this is exactly why we have to be so incredibly precise with how we measure things. In our everyday lives, we use relative temperature scales, Fahrenheit and Celsius. But when we're dealing with strict thermal systems and hard science, we switch to absolute temperature scales, like Rankine for English engineering or Kelvin for SI systems. Why? Because absolute scales start at absolute zero. That is the mind-bending point where all that internal microscopic motion we just talked about completely stops.
Moving right along to Section 3, the science of refrigeration.
Okay, so we know the rules. Now how do we bend them to our advantage? In everyday life, manipulating thermal energy really boils down to one simple goal: keeping a desired temperature inside a confined space. In the thermodynamics world, we call that a thermal storage area. So whether you're trying to keep your living room perfectly cool in July or making sure your freezer actually freezes, it is all about mastering that specific storage area.
And that is exactly what refrigeration science is dedicated to. To pull off this mechanical magic, we rely on three step-by-step principles. First, we absorb or reject heat by forcing a phase change, like boiling a liquid into a gas. Second, we strictly control the direction that the heat transfers. And third, we use materials with the exact right conductivity to move that heat efficiently.
We've come up with some incredibly clever workarounds using these principles. Take open cycle refrigeration. It sounds super complex, but it's really just a valved container full of liquid refrigerant. Simple, right? But it's a total game changer because it gives us a highly practical way to get refrigeration on the move, especially out in remote locations where bulky, power-hungry mechanical systems just aren't an option.
Now here is another fascinating trick: evaporative cooling. This cooling effect happens when a fluid, like water, evaporates directly from a hot surface. As that liquid turns into vapor, it physically grabs the heat and carries it away, leaving the original surface behind way, way cooler. And I guarantee you are intimately familiar with this one because you experience it every single time you break a sweat while exercising. That is your body performing textbook evaporative cooling. But here's the kicker. It's the exact same science we use on a massive industrial scale. Giant commercial air conditioning condensers outdoors use this, and it's even the primary method for cooling enormous livestock and poultry barns. It's basically nature's cooling system scaled way up by engineering.
When you look at the big picture of how we apply these systems, you realize how deeply tied they are to our survival. We use heat pumps, furnaces, and ovens when we need to crank up the heat, and we completely reverse the process for crucial things like food preservation, cold storage, and air conditioning. We have literally conquered the thermal storage area.
But hang on a second. We figured out how to move heat around, force phase changes, basically play God with temperature. But what is the catch? What does it actually cost us to do all of this heavy mechanical lifting?
And that brings us to our fourth and final section, thermal systems and power.
The cost of all this magic? It's power. And in thermodynamics, power isn't just some vague buzzword for strength. It has a strict, non-negotiable definition. It is the amount of work performed in a given amount of time. See, moving heat from a low-energy state to a high-energy state totally fights the natural flow of the universe. So to force it to happen, you have to do work, and work requires power.
Because of that rule, there is this massive, unseen balancing act happening all around us, every single second. Some thermal systems are purpose-built to produce power, like a massive electric station burning tons of fuel to generate electricity. But on the flip side, other thermal systems are designed to consume that exact power. Your refrigerator at home? It's sitting there right now, constantly eating up energy just to do the hard work of pulling heat away from your leftovers.
And whether that power is being cranked out by a giant power plant or quietly sipped by the appliances in your kitchen, we quantify all of it using one vital unit, the watt, represented by a capital W. It is literally the currency of the thermodynamics world. So, as we wrap up this explainer today, having gone from the frantic, invisible motion of tiny particles all the way to the watts ticking away on your power bill, I want you to try something. Take a quick look around whatever confined space you're sitting in right now. Between your AC, your fridge, maybe the computer you're watching this on, how many invisible watts do you think are currently battling the fundamental laws of the universe just to keep you comfortable today?